Let's look at some more of these counting questions. So, how many 8-bit strings have exactly 3 ones? Now, we talked about 8-bit strings back when we did permutations, but here we're doing something a little bit different. We want these 8-bit strings to have exactly 3 ones. So I have 8 positions. And in these 8 positions, I need 3 ones and 5 zeros to be put into these positions. Really, after I place the ones, the zeros are forced into their positions. So really all I've got to do is select which positions the 3 ones go in. So this is really like a combination question. I have 8 positions in total, and I need to select 3 of them to place the ones into. So it'll be 8 choose 3. So 8 factorial over 3 factorial times 5 factorial. So let's simplify this. So 5 factorials will cancel here. And this 3 and this 2 will cancel with this 6. So it's just going to be 56. So there are 56 8-bit strings that have exactly 3 ones in them. So now we're thinking about positions and placing numbers in these positions. And this is a really powerful idea because now we can look at those word problems where we arrange letters, but now where they have repeated letters. Consider the various ways of ordering the letters in the word Mississippi. How many distinguishable orderings are there? So if you think about it, the hard part is like the letters I, you can't distinguish them between each other. So this isn't just a straight like permutation problem because I have objects that are indistinguishable from each other. And so how many letters are there in the word Mississippi? There are 11. So think about it with 11 positions, and then you're going to place the 11 letters are placed in these positions. So there's like a first position, second, third. And so we're going to break this down into a step-by-step process like we've done on some other problems. So step 1, the first thing you're going to do is you're going to choose where the S's are going to go. So there are 4 S's, so you're going to choose a subset of 4 positions for the S's. So you're going to place the S's down. Then step 2, you're going to choose a subset. You're going to place the I's down. There are 4 I's, so you're going to choose a subset of 4 positions. for the I's. Step 3, we're going to place the P's down. There are 2 P's, so you're going to choose a subset of 2 positions for the P's. And then finally, there's one letter we haven't done, which is the M. So your final step is choose a subset of 1 position for the M. So now we're going to break this down. We do it in the step-by-step process, and you're going to use the product rule for counting. So the number of distinct ways to position the letters. Well, first, if I look back at step 1, I have 11 positions and I need to choose 4 of them. So it'll be 11, choose 4. But now I've used up 4 of the positions, so now there's only 7 positions remaining, and I need to choose 4 of them for the I's, so 7, choose 4. Well, now in total I've used up 8 of the positions, so that means I only have 3 remaining, and I gotta choose 2 of them for the P's. And finally, I have 1 position remaining and I need to choose 1 spot. So 1, choose 1. And now we're going to simplify this. 11 factorial over 4 factorial times 7 factorial times 7 factorial over 4 factorial times 3 factorial. 3 factorial over 2 factorial times 1 factorial. 1 factorial over 1 factorial times 0 factorial. And now we get this nice cancellation happening. 7 factorials cancel, the 3 factorials cancel, the 1 factorials cancel. So in the end, I'm getting 11 factorial over, and 0 factorial is just 1. So I can cancel that away. So 11 factorial over 4 factorial, 4 factorial, 2 factorial, 1 factorial. And if you simplify this, this will be 34,650. So one thing I want to mention, if you look at this denominator, look at these numbers that are appearing here. 4, 4, 2, and 1. We saw those numbers before. If you look back, we saw them and how many we had. We had 4 S's, 4 I's, 2 P's, and 1 M. So now we can state a general way to formulate these, counting these permutations. So permutations with sets of indistinguishable objects. So let's say we have m objects in total, n objects, so like 11 letters, but then within those we have so many that are indistinguishable, that are the same. So n1 are of type 1. So like in the last example, 4 of them were S's, and 2 are of type 2, and so forth. And K are of type K. Then the number of distinguishable permutations of distinguishable permutations of the n objects. This is first you pick the spots for the n type 1 objects, then from the remaining positions you choose the n where n2 is going to, the n2 objects are going to go. So it's this first formula, it's okay if we don't. I'm going to simplify it so it looks a lot nicer here. But in general, the formula, it's n factorial over n1 factorial, n2 factorial, n3 factorial, all the way up to nk factorial. So just like in the last problem, we had 11 factorial over 4 factorial, 4 factorial, 2 factorial, 1 factorial. We get that same formula in general.